Hello, thank you for being here. I'm Muthukumara Pandian Chandrasekharan from CTS Tech. My topic today sits at the intersection of quantum computing and automated machine learning. I want to show you how two separate efficiency ideas, multi-fidelity optimization and quantum Bayesian optimization, can be unified into a single algorithm I call MF-Q-GP-UCB, and why that combination has been missing until now. Let me start with where the cost lives. Automated machine learning takes the human expert out of model selection and tuning. But inside the pipeline, hyperparameter optimization is a single dominant cost. The reason is simple. To score one configuration, you have to train a whole model and measure its validation performance. So the objective you are optimizing has four uncomfortable properties. It is expensive because every evaluation is a full training run, and it is non-convex with many local optima. It is high dimensional with knobs that interact, and it is gradient free, a, a pure black box with no derivative to follow. This gets sharpest in the modern settings where each evaluation is a full training run of a deep learning system coupled with multi-agent reinforcement learning. And reinforcement learning is itself high sensitive to its own hyperparameters. So the number to hold in your head is 1. One full training run per evaluation. That is the cost we are trying to beat. Two research programs attacks this cost from different directions. On the left is multi-fidelity optimization. The idea is to use cheap approximation of the objective, a model trained on a subset of the data or for just a few iterations, to throw away the poor regions of the space first and only spend the expensive exact evaluation on a small promising region. This family includes MF-GP-UCB, BOCA, successive halving, hyperband, and BOHB. It is well established, but it is entirely classical and gains nothing from quantum estimation. On the right is the quantum Bayesian optimization. Here, quantum amplitude estimation reaches additive error of order 1 over n against the classical Monte Carlo rate for 1 over root n. That quadratic improvement lets QGP-UCB attain a polylogarithmic regret below the classical root t lower bound. But these methods are single fidelity and they assume the objective can be queried coherently. These two lines have matured in parallel and they have never met. So, why they never met? The reason is precise, and it is the heart of this talk. The quantum regret guarantees all assume one thing: coherent quantum access to the objective. You have to be able to put the objective into superposition and query it. Now, look at what the HPO evaluation actually is. It is a full classical training run, and a trained model cannot be placed in superposition. So the query count advantage that quantum estimation promises never turns into real wall clock advantage. There is a fundamental mismatch that I'm showing here. What a classical training run is. On the left is simply not what the quantum oracle needs. On the right, the oracle needs a cheap object that can be evaluated coherently. And the quantum HPO papers that do exist sidestepped this entirely. They either designed quantum models or applied tensor methods to the configuration kit. None of them accelerated the classical outer loop. That gap is what this work closes. Here is the whole idea in one sentence. The low fidelity surrogate is exactly the affordable, coherently evaluable object that amplitude estimation needs. Let me unpack that in 3 steps. First, low fidelity is cheap. A model trained on a small dataset subset or for only a few iterations is cheap to represent and cheap to evaluate. Second, this is the key link. That same cheapness is what make it plausibly loadable into quantum state. So amplitude estimation can act on it. Cheap is what makes it coherent. And third, the expensive exact fidelity is not thrown away. It is held in reserve, used rarely, only to refine the optimum without bias. So the punchline is this: multi-fidelity scheduling is not an efficiency add-on bolted onto quantum Bayesian optimization. It is a mechanism, the bridge that makes the quantum precision gain reachable inside the practical HPO loop. This table places the work against the closest prior methods along 3 axes. The first axis is whether the method is fidelity aware. The second is whether it uses quantum precision. Classical multi-fidelity methods like MF-Q-GP-UCB and the hyperband have the first but not the second. Quantum methods like QGP-UCB and QMC kernel UCB have the second but not the first. But look at the third column, which is the real contribution. It asks whether the method supplies the coherently evaluable oracle to the quantum estimator, rather than just assuming one exists. The quantum methods assumes it. No prior method provides it. So MF-Q-GP-UCB on the bottom row is the only method that occupies all the 3. Fidelity aware, quantum precise, and it actually builds the oracle through the low fidelity. Let me state the setup formally quickly. We have a compact configuration space and an objective F with bounded RKHS norm under the known kernel. We are seeking its maximizer observed only through noisy, costly evaluations. There are M fidelities ordered by increasing cost and decreasing bias, and the top fidelity is unbiased. Crucially, each fidelity has a quantum mean estimation oracle through amplitude estimation. It returns a reward mean estimate to additive error epsilon using order 1 over epsilon quantum queries. In place of the order 1 over epsilon squared classical samples, and I measure cost by what I call capital, which is the cumulative training cost of the fidelity query. The goal is small, simple regret for a given capital budget. So everything is indexed by capital, not by iteration count. Now the algorithm itself, MF-Q-GP-UCB, is a single loop with 3 interacting components. It goes like this. We fit one Gaussian processor posterior over the objective using the observations gathered across all fidelities. The acquisition rules then proposes the next configuration to try. The switching rule chooses which fidelity to evaluate that configuration at. Amplitude estimation produces the observation at that fidelity. And we update the Gaussian process and charge the capital we spent. Then we repeat until the budget is exhausted and return the posterior mean maximizer. The 3 roles are worth naming clearly: the surrogate models the objective across fidelities, the acquisition proposes where to look next, and the switching run on the rules chooses the fidelity that feeds the quantum oracle. The third role, switching, is where the novelty lives because it deliberately routes cheap fidelities to the quantum estimator. Let me take the 3 components one at a time. Component 1 is the multi-fidelity surrogate. a single Gaussian process model the target objective. The trick is how each observation enters the posterior. Its noise variance has two terms. The first term is the estimation error, epsilon square, which is how the precise the amplitude estimate is. The second term is the fidelity bias bound, zeta square, which downweights the biased low fidelity observation in proportion to how far it might sit from the truth. So the bias cheap point is still informative, but it is discounted. You can see that on the right. The elegant part is that treating the fidelity gap as inflated observation noise, let us keep one single posterior over the objective instead of fitting the separate model for every fidelity. Component 2 is the quantum refined acquisition. The selection rule itself, nothing exhaustive. It is the standard upper confidence bound with the usual logarithmic exploration schedule. The quantum element does not change how we select, it changes how we measure. Classical Monte Carlo needs order 1 over epsilon squared samples to reach the precision epsilon. Amplitude estimation reaches the same precision in only order 1 over epsilon queries. That is the quadratic gain. So the confidence interval at the chosen point contracts at the quantum rate and the exploration term. This is how we get below the classical lower bound. Component 3 is fidelity switching, and this is the rule that ties everything together. It decides where each configuration get evaluated. There are two cases. Near the current incumbent, the best point so far, we use the exact fidelity. Why? Because refining the optimum demands an unbiased estimate, and only the top fidelity gives us that. Away from the incumbent, we can use cheap fidelity whose bias bound is dominated by the current posterior width. This is the classic multi-fidelity principle. The query low fidelities while your uncertainty is large, and escalate to the exact fidelity as that uncertainty shrinks. That brings us to the theory. Theorem 1 says the following: under RKHS and Oracle assumptions, and provided the switching rule only, queries a low fidelity where its bias is dominated by the posterior width. MF-Q-GP-UCB attains a cumulative regret of the order polylogarithmic in T. That matches the single fidelity quantum rate, and it sits below the classical root T lower bound. At the same time, the capital it spends is strictly less than what single fidelity QGP-UCB would spend. The proof itself is a composition joining the staged quantum confidence contraction from QGP-UCB with the multi-fidelity bias control from MF-Q-GP-UCB. The full accounting is in Appendix A. Let me be very clear about how I evaluate this, because it matters. I do not use quantum hardware. What I model is the one primitive that actually carries the quantum regret result, which is amplitude estimation precision. Concretely, each evaluation is given a fixed short budget n. At that budget, a classical observation carries noise of sigma 0 over root n, while the quantum observation carries sigma 0 over n. So at equal query count, the quantum estimate is quadratically tighter. That means I report a query complexity and a simulated precision advantage, and I state that caveat openly. I compare 5 methods, holding everything fixed except 2 things: fidelity awareness and estimation precision. And I use 2 benchmarks. One is control synthetic surface, so I know the ground truth. The other is a real clinical HPO task, turning kernel ridge regression on the diabetes progression dataset. Both use only public data and shared scripts, so the results are reproducible. Here's the first result on the synthetic benchmark. This is simple regret against capital on a log scale. So the lower is better, and the left side is the budget limited region where expensive HPO actually operates. Watch the coral curve, which is the combined method. It drops fastest and it sits lowest exactly where the budget is tight. Put a number on it. At a capital of 100, my method reaches the regret of 0.0039, while the strongest baseline is still up around 0.2. That is roughly 50-fold difference. And the two effects are cleanly separatable in this picture. Multi-Fidelity buys the early progress through cheap exploration on the left. So the advantage here is the capital efficiency under constrained budget, not a lower asymptote. The clinical task tells the same story, but now with the real model in the loop. I'm turning kernel ridge regression on diabetes progression, optimizing the regularization strength and the kernel width, and the fidelity is the fraction of traction data we use. Here our combined method is the lowest curve at every single budget, not just one regime. That gives the regret landscape real spread, which means the separation between the methods is informative and not just noise near a floor. Two ablation test whether the mechanism behaves the way the theory predicts. The first varies the short budget n, because classical error falls as 1 over root n and the quantum error falls 1 over n. The quantum advantage should grow as n grows, and it does. So my regret drifts up from the floor toward the single fidelity quantum value of 0.042, which never queries a low fidelity and so never moves. That confirms the bounded gap condition is a real boundary of the method, not a technical convenience. Let me be candid about scope, because that is what makes the result usable. You should expect a benefit when three things hold together. One, the exact evaluation is expensive, while cheap, low bias, roughly monotone fidelities are available. Two, the estimate near the optimum is limited by measurement noise rather than model bias. And three, the capital budget is genuinely constrained on a winning landscape where most configurations are near optimal. Nothing separates, and that is fine. And the limitations are real and worth stating. The quantum advantage is modeled at the precision level, not demonstrated on hardware. So the gate error and the cost of loading the oracle are omitted. The RKHS assumption weakens in high dimensions. The surrogate uses the simple inflated noise fusion, and capital is a cost proxy, not measured wall clock time. So to close, the one idea is to take away is that multi-fidelity scheduling is the bridge that carries quantum precision into practical HPO loop by supplying the coherently evaluable oracle that quantum Bayesian optimization assumes, but earlier methods never built. There are three contributions: the bridge itself, a cost indexed regret analysis, an explicit bound gap condition, and empirical evidence that combination reaches the target accuracy with less capital, most clearly under the tight budget that characterize expensive HPO. Looking ahead, the open directions are tighter constants without the bound gap assumptions, a hardware aware oracle, high dimensional extensions through deep kernels, and continued fidelities. So applying this is to tune the expensive multi-agent reinforcement learning. Thank you for your time. I would glad to take your questions through email.